All right, hi everyone. So we're gonna do benzylic oxidation. So you should remember what this means. We went over it in a recent session, but if not, here we are. This is a very important concept that's actually not too difficult. It's just one main rule that applies to several situations. So this is oxidation of a side chain basically on a benzene ring. So if you've got a benzene, right, the benzylic position is that carbon that is directly attached to the benzene ring. So this would be your benzylic position, right? So for this reaction, you can use, the reagents would be either the Jones reagent, right? So the Jones reagent is what? It's K2 Cr2O7, right? Or, you know, the Na version, so the sodium chromate, or this is potassium dichromate, right? So you can use that with H2SO4 and water, or, right, so this is Jones, okay, or you can use potassium permanganate, which is KMnO4, and water and KOH, right? So if you realize this approach is basic because of the KOH, and the other approach would be acidic because of the strong acid H2SO4. Okay? So you don't need to know the mechanism for this one. However, you need to know the requirements. So what you need in order to actually use this reaction, to use these reagents, excuse me, and basically gives you a carboxylic acid. So it helps us out a lot in case we need, so one way that you could use this, like one way it would be helpful, is if you're doing synthesis, right? And you'd like to use a meta-director, but you are starting with an ortho-para-director, because this is this, obviously you have a CH3, this is a methyl group, so you have a CH3 on benzene, this is actually called toluene, right? So this would be an ortho-para-director because this is an electron donating group, but if you want a meta-director for your synthesis, this is a meta-director, right? Because it's an electron withdrawing group due to the carbonyl presence, right? So that would help you in that regard, okay? So essentially, so let's just make a little note here. This oxidizes the benzylic position to carboxylic acid, right? So again, the definition of this, of oxidation, is more bonds to oxygen, right? Which we can obviously see from here to here. There's more bonds to oxygen than there was here. And you need hydrogens to do that, okay? You need to use up those hydrogens. So if you don't, so here's another note. If you have no H's in the benzylic, so on benzylic position, then you can't do this, right? You can't do it. So let's see some examples. So the one from the notes, one of them looks like this, okay? So that's an ethyl attached, okay? So we use KMnO4, let's say, KOH and water. And what do we get? What do we think? Cool. I hope you all said you get a carboxylic acid, because that's the point of this, right? Now, one of your questions might be, well, this is different than this, right? So does it not matter what the side chain is, really? And the answer is yeah, it really doesn't matter. So the reason's because, so here's some H's, right, at this position. On this position, we have 3, right, because it's a methyl group. you really just need one hydrogen at the benzylic position in order to oxidize it to the carboxylic acid. So you'll have, so basically this part of the side chain will be degraded. Okay, so we say it's degraded. And we get to our carboxylic acid product. Okay, so one more time, you must have benzylic protons for the oxidation to occur. Okay, you must. So what if though you had this, for example, tert-butyl attached, right? And you do the same thing, what will you get? Good job, everyone. Nothing, right? There'll be no reaction. And why is that? Because there are no H's at this benzylic position, right? So that's something to keep in mind. Okay, this can be really helpful for synthesis planning, as I mentioned before, because now so instead of an electron donating group, you have an electron withdrawing group. I hope that was helpful. Click ahead to the next video.